So let's continue on with another set of examples. Again, we have an A, B, and a C here. And we're just sort of continuing to use some of the strategy we've looked at so far. These integrals might appear a little bit more complicated though, so it's good additional practice. Let's start with part A here. I had to write in that x. For some reason this didn't come out when I printed it, but that's fine. So we're looking at the integral of the natural log of x over x. Now, at first glance, this might look like this third case that we looked at here, where it looks like a rational function. It's not actually a rational function, though. Even though it's a quotient, my numerator is not a polynomial. Rational functions have polynomials in the numerator and denominator. That doesn't necessarily mean just by itself that it's not a good idea to let our denominator be our u, but I can see already that wouldn't help, right? So if I set u equal to my denominator x, then my du is just 1, and nothing has accounted for this much more complicated function up here, the square root of the natural log of x. However, paying a little closer attention to that numerator, the square root of the natural log of x, that is a composite function all by itself, right? Because the outer function is that square root and the inner function is that natural log of x. And if you remember where we started with this section, the inside function is generally the thing that we want to be calling u. So I have a hunch that if we set u equal to the natural log of x, that is going to be what's most helpful here. So let's see what else we get out of this. U is equal to the natural log of x. We know what that means du is equal to. The natural log has a derivative of 1 over x, so I get 1 over x dx. And notice that x is in the denominator just like it is over here. So really what we have, you can think of this this integrand as the square root of the natural log of x times 1 over x. It's the same thing. So we actually have something pretty close to, or pretty useful here. If I rewrite this in terms of u, it's not just u up here, it's the square root of u. So I actually have the square root of u. But then again, we said that we can think of this as the square root of the natural log of x times 1 over x dx, which that whole thing is equal to du. Now I have the square root of u du. This is not difficult to take an antiderivative of. We know how to do this. Just as a reminder, it's useful to rewrite it in terms of a rational exponent first, so that I can see how I would use the power rule in reverse to find an antiderivative. Add 1 to the exponent, which is 3/2. Multiply by the reciprocal of that new number, which would be 2/3. And then don't forget your plus c. Finally, now that the integral is done, replace the u with the thing we set it equal to. So this is 2/3 times the natural log of x to the 3/2 power plus c. Okay? Wasn't that difficult, but again, we kind of had to think through what the best choice of u would be in this problem. Okay, so let's try part B now. Part B looks relatively complicated, but it has a somewhat familiar form based on what we looked at previously. There is an exponential function in there, and the exponent of that exponential function is something more complicated than just x. So in those cases, we said it's probably most useful to set that exponent equal to your u. Let's try it and see if that helps. I'm going to set u equal to x cubed plus 2x squared. Okay, which means du would be equal to 3x squared plus 4x, but that whole thing is multiplied by dx. Remember, you always get that dx that shows up there. And if I have more than one term present here, I need to put parentheses around it to show that it's that entire function times dx and not just one of the terms. Compare that to what we see in our function. In my function, I have something, or my integrand rather, I have something that looks very similar to this. Instead of 3x squared plus 4x, though, I have 6x squared plus 8x. But if you notice, if I were to just multiply this entire function by 2, I would get this. So let's multiply both sides of this by 2. 2 du equals 6x squared plus 8x dx. So now I can see that the 6x squared plus 8x and this dx together can be replaced by just a 2 du. And again, when we rewrite our integral, that 2 can be pulled out. So that's going to account for the 2. The du I'm going to write at the end. But what else is left in here? 5 to this exponent, which is what we defined u to be. So 5 to the power of u, and then there's the du that I needed. Much simpler looking than what we had initially, right? So how do you take an antiderivative of this? Well, again, think about how you would take a derivative of this. The derivative of an exponential function is just that same exponential function times the natural log of its base. But we're doing the reverse of that. We're taking an antiderivative, and what that amounts to is that instead of multiplying by the natural log of 5, we're dividing by the natural log of 5. So that would be 1 over the natural log of 5, or if I multiply this 2 here, I could write it as 2 over the natural log of 5 times 5 to the power of u plus c. And then again, as a final step, anywhere I see a u, I replace it with that corresponding function of x. So 2 over the natural log of 5 times 5 to the power of x cubed plus 2x squared plus c. Okay? And that's it. That's the whole thing. I keep saying it, but I'm going to keep saying it anyways. It's a good idea for you to check your answer by taking the derivative of your result and making sure that you get the integrand that you started with. And as before, I'm going to leave that part to you. Last up is part C. Part C looks rather complicated, but we've now developed some kind of common things to look for to help with our selection of u. So we have the integral of 2x to the 4th over the cube root of 8x to the 5th minus 9. Okay, so looking at this, I have something that's close to a rational function, but it's not exactly a rational function because the denominator is not actually a polynomial. In fact, it is a composite function. It's a polynomial inside of a cube root function. And the fact that I see a composite function there is what really gives me my hint as to what I would choose for my u. Because remember, if you see a composite function in there, it's generally a good idea to set the inside of it equal to u. Whereas here, the inside would be 8x to the 5th minus 9. I'm going to try setting u equal to 8x to the 5th minus 9. And what's convenient about this is I have a 5th degree polynomial. As we have seen before, when I find my du, I'm automatically going to have a 4th degree polynomial, and my numerator is also a 4th degree polynomial. So my gut tells me that this was the right choice to make. What is du in this case? Well, 5 comes down, multiplies to the 8, that makes 40 x to the 4th dx. As we've seen before, that constant does not match the constant that I actually want to be seeing there. I need to get a 2. So we fix that by multiplying both sides of this by something that will turn that 40 into a 2. 1/20th will do that. So if I multiply both sides by 1/20th, remember that's like dividing by 20, I would get 2x to the 4th du. I get the thing that dx. That should be a dx. It's the second time I've done that. That is what I should be seeing there, okay? So putting all of this together now, this becomes the integral that 1/20th I can bring out side like we've been doing, okay, times the integral of what? Well, I know that the 2x to the 4th dx all together is going to turn into a du, and I'll save that for the end. But then I'm going to have 1 over the cube root of u. U was just the inside of that, so it's actually the cube root of u du. Okay? This I can take the antiderivative of, but it's going to be helpful to change the representation that I'm using. So this is u to the 1/3 power in the denominator, and because I have that in the denominator, I could write this as u to the negative 1/3 power du, like that. Okay? Add 1 to the exponent. That's going to give you u to the 2/3 power. Okay? Then multiply by the reciprocal of that new exponent, which would be 3/2. There's already a 1/20th out there. So 1/20th times 3/2 would be 3/40 plus c. Okay? And then last step, replace u with your function of x. So 3/40 times 8x to the 5th minus 9 to the 2/3 power plus c. That is my final answer. Okay? So again, the general things to look for that we talked about on the previous page was partially helpful here. But as you can see with u substitution, sometimes there's not, well, not sometimes, pretty much always, there's not a universal rule for how to choose u. There's just some general guidelines. So we've seen that, exponential functions, it's been helpful a couple of times to choose u to be equal to that exponent. But other times, it's helpful to look for something in your integrand that looks like a composite function, something where there's a function inside another function, and then you set that inside function equal to u. That's also been helpful, okay? But again, sometimes that will fail also. So just be aware that u substitution will sometimes require trial and error, okay? All right, let's move on to these. So in this case, sometimes when we do a u substitution, you might need to do some algebraic manipulation with your choice of u, not just the du. We have now seen multiple times, let's go back here, that you may get a du that does not exactly match what you want. You don't want du in this case to be 40x to the 4th. We wanted it to be 2x to the 4th dx. So we manipulated this equation a little bit so that we had it in the correct form. But sometimes you also have to manipulate this expression here. And so that's kind of what I'm referring to with this guy, okay? Now, it's not going to be the case for every single one of these integrals, but it is going to pop up. So I'll point that out when it does. Let's start with this one. I want to evaluate the integral of e to the 5x over e to the 5x minus 1. Now, one thing we have said is that in the case of exponential functions, it can be helpful to set your exponent equal to u. But notice I would be setting two different exponents equal to the same u. It would say e to the u up here, and then e to the u down here. And even though that might look a little simpler than what we have, it's not simple enough to make this solvable with the techniques that we have covered so far. So we need to think of a different way of choosing u. Now I'm going to use something that I know about the exponential function. The exponential function e to the x is equal to its own derivative. And if I have like e to the 5x, for example, I would use the chain rule on that. So e to the 5x is not its own derivative, but it's almost its own derivative. So something tells me that if instead of choosing 5x to be my u, if I choose an expression that involves the entire exponential function and set that equal to u, I think that is going to be more useful. In fact, what I'm going to do is take my entire denominator and I'm going to set that equal to u. We've seen this before. This has been helpful before. E to the 5x minus 1. If that's the case, what is du equal to? Well, from the chain rule, e to the 5x, this is a composite function. I multiply by the derivative of that exponent, which is just 5. And then I have the same exponential function, 5 e to the 5x dx. That's what the du would be. Notice if e to the 5x minus 1 is u, then this entire denominator is u. And then my numerator, e to the 5x, is also making an appearance there. The only unaccounted for thing is this 5. That's an easy fix, and by now we definitely know what to do. We multiply both sides by 1/5. So we get 1/5 du equals e to the 5x dx. Oop, the dx does not belong up there, sorry, dx. That accounts for this numerator and the dx there. Then I have a u in my denominator, so this whole thing turns into 1/5 times the integral. Now I'm going to use a notation that I have not used yet, but it is actually a fairly common notation. E to the 5x times dx, that's 1/5 du. I already accounted for the 1/5. The du I can put in the numerator if I want to. When we've done this before, where I set my denominator equal to u, I wrote it as 1 over u, and then I put the du out here. But this is also an acceptable notation, which means the same thing. My entire denominator was u. Okay? This is where we get our natural log function. So this is equal to 1/5 times the natural log of the absolute value of u plus c. Now I'm going to replace that u with my exponential function. So this becomes 1/5 times the natural log of the absolute value of e to the 5x minus 1 plus c. That's my final answer. All right. So far, so good. Let's take a look at another example. So B. I should label that A. Here's B. I want to take the integral of x over 4x plus 5. Now, at first glance, this may not seem that complicated. We have dealt with more difficult looking rational functions as integrands, but there's something important about this example that makes this a little harder than it might initially look. So to see why, I want to revisit one of the previous examples that we did, all the way back here. So we did this example where we had a rational function. And in that case, we saw that setting our denominator equal to u was the most helpful approach. And that's because when I found my du, it accounted for the entire numerator and that dx after a small manipulation on that equation there. But a key thing here that we pointed out was that the degree of my numerator was 1 less than the degree of my denominator. That's what made it kind of naturally show up when I found that du. That's actually not happening here. So here, the degree of my numerator is actually the same as the degree of my denominator. So that x will not naturally appear as my du. What do I do about that? Well, it turns out that we still want to set u equal to our denominator, but there's going to be a little bit of manipulation that has to happen to that equation u equals 4x plus 5. And we'll see what that looks like in just a second. Let's find du really quick. Du is just 4 dx. So here's the dx. It matches, but there's no 4 showing up in my numerator. This 4 is not important because that's going to become part of the u. It's not part of the du. So really all I have left is x dx. I don't have the 4 that I want. So I can multiply both sides by 1/4 to get rid of it. 1/4 du equals dx. I can't multiply both sides of this by x to force this x to appear here. And the reason why is because at the end of all of this, I want to have this integrand entirely in terms of u's. If I try to multiply both sides by x after this step to get an x dx here, then I would also have an x over here in the thing that I'm going to use as my substitution. So that's going to introduce another x that I don't want to be there. So instead, I have to figure out what am I supposed to do about this x in my numerator because it's not appearing anywhere else. Well, in the work that I've done here, the only place that x appears by itself is right here. And it's related to u by this equation. Notice, if I wanted to, I could solve this equation for x. I would start by subtracting 5 from both sides and then dividing by 4. Or that's the same thing as multiplying by 1/4. That's the same thing as 1/4 times u minus 5 in parentheses. Okay, notice this is what I would get from here by solving for x. So this expression is equal to x, which means it can be used as a substitution for this x right here. And if I do that and make the other substitutions that I've found here, then the entire thing is going to be put in terms of u. So let's think about what that would look like. Okay, now my new integral is going to look like this. We have a 1/4 du, and the 1/4 can come out of your integral like this. Okay, and then my numerator, which was just x before, turns into this, 1/4 times u minus 5. My denominator, remember my entire denominator is what I chose to be equal to u, right? And then after that, we have dx, which is equal to 1/4 du. The 1/4 we already wrote out here, so that means I just have a du. Notice how my integrand does not involve any x's anymore. It's only got u's in it. That's what I wanted, right? I can evaluate this, but I have to simplify it a little bit. So the 1/4 here can be brought out of the integral. It would multiply with this 1/4 and give me a 1/16, like this. What I'm left with is u minus 5 over u du. Now this, even though it doesn't look that much simpler than what we started with, what's convenient about this one is that where the variable appears by itself is in the denominator as opposed to the numerator. And the reason that's helpful is because I can split this into two separate terms. I can write it as u over u, which is really just 1, minus 5 over u du. Okay? From here, solving this is not that hard. This is equal to 1/16 times, remember with integration you can do each term separately. You can split this up into the integral of 1 du minus the integral of 5 over u. But rather than write that out as an additional step, I'm just going to do that in my mind. So the integral of 1, remember this is all in terms of u, is just u. And then minus 5 over u, if you pull that 5 out, it's really 5 times 1 over u. 5 times 1 over u, but the antiderivative of 1 over u is the natural log of the absolute value of u. So that's what that becomes, plus c. Then as a final step, make the replacements that we need to make. So instead of u, we're going to write 4x plus 5. This is equal to 1/16 times 4x plus 5, that's the u, minus 5 times the natural log of the absolute value of 4x plus 5 plus c. That's my final answer right there. Okay? It is not uncommon for integration problems to give you kind of complicated looking functions. So don't look at this and think that looks too complicated. I probably did something wrong. That's not an indication that you did something wrong. That is what happens oftentimes with integration. It's just part of what we're doing. Okay, one more to go. This function looks kind of similar to something we have seen before. So I'm going to return to that example really quick. It looks kind of similar to this integral right here, where we have a polynomial in parentheses raised to a big power and then multiplied by something else on the outside. In this case, it was helpful to let u equal the thing in parentheses, x cubed minus 5, so that when we took the derivative of that, our du, we got a second degree polynomial, which accounted for the du out here. Okay, this guy looks pretty similar. We have a polynomial in parentheses being raised to a power, which suggests that I should let u equal the thing in parentheses. The problem here is that if I found my du, I'm going to get a first degree polynomial, not a third degree polynomial. So something has to be done to account for that. And we'll look at that here. So I'm going to go a little bit off screen, but the set of parentheses here suggests that I should take 4x squared plus 9 as my u. So let's do that. 4x squared plus 9, which implies that du is equal to 8x dx. Okay? Now, I'm seeing an 8 here where I am not seeing one here. So I'm going to do what we've been doing a lot of up until this point. I'm going to get rid of the 8, and to do that I'll multiply both sides by 1/8. So I have 1/8 du equals x dx. Okay? Now, how do I get this x cubed here? Well, at first, your first guess might be to say that let's just cube both sides of this, right? And then that will take care of that x cubed. But the problem is that if I cube both sides of this, I would also be cubing that dx term. And I don't see a dx cubed up here. I see just a dx there. That's not going to do it. So instead, what we want to do is think of this x cubed term as x squared times x, right? X squared times x is equal to x cubed. And if I think about just this x here together with this dx right here, that's what I'm seeing here. So together, those two things are equal to 1/8 du. We know that the 1/8 is easy to deal with. It comes out of the integral. So this will be accounted for in my du term. But there's still the question of this x squared here to deal with. Well, fortunately, that x squared has an appearance over here. X squared is related to u by this equation. If I solve for x squared, I would be subtracting 9 from both sides and then dividing by 4. So I would get x squared equals 1/4 times u minus 9. Okay, so this x squared I can replace by this expression here, 1/4 u minus 9. Let's do all of those substitutions in this integral right here. So I'm going to be going kind of a little back and forth. So again, this x squared, which is part of the x cubed here, is going to become 1/4 times u minus 9. That was being multiplied by an x dx, which is the same thing as 1/8 du. Let's take the 1/8 and pull it all the way out, and then the du I'm going to save until the very end. We always write that at the end. And then I have 4x squared plus 9 to the 12th power, but the 4x squared plus 9 we define to be equal to u. So this is now u times 12, or sorry, to the power of 12. And then here's the du that I was saving until that point. Okay? So let's do this. Let's take the 1/4 here, bring that out. That'll multiply to the 1/8 and give me 1/32 times the integral of, then I have this u minus 9 times u to the 12th power. But I can distribute that u to the 12th power in here. U to the 12th times u is u to the 13th power, minus this would be 9u to the 12th. And now I have a really simple polynomial, and those are like our favorite things to take derivatives and antiderivatives of. So this becomes this, 1/32, add 1 to the exponent, and then multiply by the reciprocal of that number. That would be 1/14, u to the power of 14, minus 9 times u to the 13th, add 1 to the exponent, multiply by the reciprocal. So if I multiply by 1/13, I would have this 9 still here. That becomes 9/13 u to the 13th power plus c. And then finally, you know what the last step is. Take any u's in this expression, replace them with this expression in terms of x. So this is equal to 1/32 times, let's go like this, 1/14 times 4x squared plus 9 to the 14th power minus 9/13 times 4x squared plus 9 to the 13th power, and then out here plus c. Again, it might throw you a little bit to see how complicated our answer looks, but that is very typical of this type of integration problem.